Hello, everyone. It's my great pleasure to introduce our next plenary speaker at the Brazilian Mathematics Colloquium, Jordan Ellenberg, professor of mathematics at the University of Wisconsin-Madison. Jordan works in the research fields of number theory and algebraic geometry. He has received several distinctions, including being a fellow of the American Mathematical Society and a Guggenheim Fellow. Jordan is also a science communicator and has recently launched a new book, Shape, the Hidden Geometry of Information, Biology, Strategy, Democracy, and Everything Else, which I am really enjoying. His previous book, How Not to Be Wrong, The Power of Mathematical Thinking, has been translated to Portuguese, so também está disponível em português, O Poder do Pensamento Matemático, A Ciência de Como Não Estar Errado. Today, Jordan will tell us about upper bounds for rational points. Jordan, thank you so much for accepting our invitation. The floor is yours.
Oh, thank you so much for bringing me. And I guess this is my second visit to IMPA, but it was much more fun the first time I came to IMPA when I could actually be in Brazil. And I hope that next time I will be able to come again soon. By the way, I want to add, as Carolina was nice enough to say, that the book How Not to Be Wrong was translated in many languages, but Brazil was the very first place to make us an offer before the book even came out in the United States. So I was very impressed with the Brazilian publishing industry and the Brazilian public's interest in math, because they jumped first to say, like, we want the Brazilian rights. But today, I want to tell a story about number theory and algebraic geometry. And depending on how fast we go, maybe I'll talk about a new result of myself and Brian Lawrence and Akshay Venkatesh. But I really want to start from the very beginning. I want to start by talking about what is this subject Diophantine geometry that I spend most of my day working in, this subject of the interface of number theory and algebraic geometry. And the question is basically this. I give you an equation. An equation means an equation in polynomials to some number of variables. Here I wrote one down. Y squared minus xyz plus z squared equals x cubed minus 5. And then the question is, what are the solutions to this equation? Because I'm a number theorist, when I say solution, I mean solutions in numbers, like the one in Chronicles words that God made, the integers. How can I choose x, y, z integers to make this equation hold? And why did I write this one down? Because I actually looked up a thread on Math Overflow on like simple Diophantine equations where we don't know the answer. So the answer is we don't actually know what the solutions to this equation are. I mean, I don't want to make it sound like we know nothing. I mean, there's a long history. A lot of famous problems in mathematics are in this form. I mean, for instance, going all the way back to the very dawn of geometry, the question of what integers can be the side lengths of a right triangle, satisfying Pythagoras' equation, a squared plus b squared equals c squared. That leads us to ask, if we're interested in what are all the right triangles that can have integer side lengths, what are all the solutions of integers a, b, c, to this equation, the Pythagorean equation. Okay, that's one which in fact we can write down all the solutions to, which is a beautiful piece of elementary mathematics. Maybe I'll mention, because this is going to come up, this is an example of something we're going to see a lot, a so-called homogeneous equation, because every single polynomial involved here has the same degree, namely 2. A squared plus b squared equals c squared. I could throw in another polynomial of degree 2, like ab or ac, and that would still be homogeneous. By contrast, here's something not homogeneous. M squared minus 2n squared equals 1. This is asking, when can the square of one number be very close to twice the square of another? This is not homogeneous, and it's worth taking a second to think about why that is. You might say, well, I see the polynomials there. M squared and n squared, they both have degree 2. But there's another polynomial, right? The constant is a polynomial. It just happens to be a polynomial of degree 0, and that counts. So this is not homogeneous because there's a degree 0 term. By the way, if we want to get like really down and dirty, you could say, well, what if I made this homogeneous? What if I just said m squared minus 2n squared equals 0? What about, I should have written this on the, maybe I will write it. See, I have the power because I'm this new world where it's an iPad. Here's the Diophantine equation I should have written first. M squared minus 2n squared equals 0. What are the solutions to that? Well, there are no solutions. because if the square of one integer were twice another, that would say that n over n equals the square root of 2. But again, one of the very, very, very earliest theorems in number theory, some would say the very first theorem ever proved in number theory, the square root of 2 is not a rational number. It cannot be expressed as the ratio of two integers. And that too is a Diophantine statement. It's a statement about this homogeneous Diophantine equation not having any solutions. This one, on the other hand, does have solutions. Maybe some of you out on YouTube even thought of one while I was like telling this historical story. For instance, you could have m equals 3 and n equals 2. And in fact, this is another equation where we can describe all the solutions. There happen to be infinitely many of them. And it's the beginning of a whole beautiful story in algebraic number theory, the theory of Pell equations, which in many ways is actually still active. I mean, I just went to a beautiful talk by Carlo Pagano, who just this year proved a wonderful theorem about for which values of 2, I mean, I had to make a choice, but of course the Pell equation is not just this particular equation. I could put any number here in place of 2, any number that's not a square that is, and I'll leave it for those who are interested to think why I say that. But Carlo Pagano, together with Peter Koymans, has a beautiful new theorem about for what proportion of numbers does this negative Pell equation, the one with -1 here, have any solutions? So even now there's sort of new stuff being proved about this. But I said a little bit about some specific equations, but the question I asked was just this overall general question. Given an equation, what are the solutions? And I wrote sort of answer with a little blank here, and let me emphasize that the answer is that we just have no idea. This problem is a complete mystery. We have no general way of looking at a Diophantine equation and telling the solutions. And to be honest, we probably never will. There's even a formal sense in which that's a theorem, like a theorem of, I guess, Julia Robinson and Matyasiewicz and sort of like people in logic and Diophantine geometry from the 60s who proved that there really isn't a way to universally solve Diophantine equations. Okay, so that problem's too hard. Is that the end of the talk? No, we got to do something. So let's see where we can go from here. All right, here's an easier question. What if we don't say, tell me all the solutions? What if we just say, how many solutions does an equation have? That seems like a much simpler question. Actually, it's probably just as hard. So this too, I'm just going to sort of, all I'm going to say about it is that question mark, question mark, question mark. And I think, and maybe somebody in the audience can correct me if this is not true, I don't actually think there's any case in which we can say the number of solutions to a Diophantine equation without telling you what the solutions are. So this on the surface looks like it might be much easier, but seems just as hard. Okay, so we're not done turning the knob, right? We have to make it easier still. That was not easy enough. So let's ask instead, and this is really the sort of what we're going to talk about today, can we at least get upper bounds on the number of solutions an equation has? Maybe I can't tell you exactly how many, but at least maybe I can tell you it has no more than so-and-so number of solutions. And that at last is a question that one can say something about, at least in some cases. And I want to sort of talk about some of the directions that that story goes. Well, by the way, I mean, it's a big area, so I'm not, for those who are fans of like the Chabot method, even though that's an area where there's like huge recent developments, I think I'm not going to talk about that today. So we'll just put a pin in that for the Chabot fans. But let me, again, for people, because this is a colloquium talk, and I don't want to assume all of you guys are marinated in the way that arithmetic geometers think about these problems. Sometimes we can make these things seem more mysterious than they are. So let me just start with a very basic heuristic that gives you some sense of what to expect. So ready? Here's a heuristic. I'm going to write an equation in n variables, which I'll label x1 through xn. And now, here's this word I mentioned before. I want it to be a homogeneous equation, which means every monomial that appears has degree d. Here, I wrote one down for you, and this one was not picked for any particular purpose. I just wrote down some random terms. Here is an equation in 3 variables of degree 4. So if there's terms like x to the 4th plus y to the 4th, and degree always means total degree in all the variables. So y squared z squared is degree 4 because 2 plus 2 equals 4. There's 2 y's and 2 z's. Of course, I changed from x1, x2, x3 to x, y, z, but it's a law that whenever you only have 3 variables, they get to be called x, y, and z, and only when you have an unspecified number do they acquire subscripts and all be called x. So let's just be kind of naive people and try to guess how many solutions this equation would have. Well, here's what I'm going to do. Considering all possible triples of integers is maybe too much to think about. I can't get my head around that. That's a huge infinite set. So let's instead work in a box. Okay, what does a box mean? I just literally mean like in R3, like a little box like this, where I put bounds on the x coordinate, the y coordinate, and the z coordinate. Let's see, can I actually draw? This is why I never teach multivariable calculus, because I'm very bad at drawing the x, y, and z axes all together. Did I do okay? This is supposed to be a box centered at the origin. So I'm saying the absolute value, so x, y, and z are all bounded between negative b and b, where b is just some bound. Okay, so how many choices of x, y, and z are there? Well, there's about b cubed. And now I hope people on the YouTube are going crazy and saying, like, isn't it like 8b cubed? Or maybe it's like 2b plus 1 quantity cubed or something like that. Let me just say we are going to be very lax about constants in this talk. So I'm really mostly going to be focused on the order of growth of various functions. So I'm not going to distinguish between 8b cubed and b cubed. It's the order of growth in b is b cubed. Okay, great. So now I've given myself lots of possible values of x, y, and z. And I'm hoping that for some of them, if I plug in that value of x, y, and z, I get 0. Then I win. Then I found a solution. If that's true for more values of x, y, and z, I get more solutions. I wonder if this one that I wrote down has any obvious solutions. I didn't think to check, but it's possible that it does. I think maybe 1, 0, 0 maybe is a solution. Okay, I should have checked, but because I wrote this equation down at random. In any event, let's think about this like a probabilist. Let's say, what is, if I plug in some random numbers between b and negative b into this equation, notice that each one of these monomials, x to the 4th, is then going to be some number whose size is around b to the 4th, right? It's sort of somewhere between 0 and b to the 4th. And again, if you're thinking, well, wouldn't it be on average like half b to the 4th? I'm not worried about the difference between 1/2 and 1. Let's just say it's about size b to the 4th. Same with y to the 4th. Same with 2xy cubed. See how it's nice and with everything homogeneous? That because x, y, and z are all roughly the same size b, each of these terms is roughly size b to the 4th. And when I add them up, maybe that's still roughly size b to the 4th. And maybe, maybe I added 5 terms, like so what? I'm not worried about the 5. So my expectation is that typically the value of f of x, y, z is around b to the 4th. Okay, so I have some integer. Its size is around b to the 4th. It might be positive, might be negative. One thing I was careful to do is write something down that was not always positive, because that would be like a very good reason for it not to have interesting solutions if this thing was like always non-negative. But I carefully put in a negative z to the 4th here to make sure that this function is sometimes positive, sometimes negative. Okay, so what do you think? You have a number between b to the 4th and negative b to the 4th. What's the probability that it's 0? I guess should be around 1 over b to the 4th. I said it was a heuristic, right? We're not proving anything here. We're just doing scratch work on the back of our envelope. Okay, so I have b cubed choices. And for each one, the probability that it's a solution, I think should be about 1 over b to the 4th, or b to the negative 4. So the total number of solutions, the expected number of solutions, if you will, in this range, inside this box, is b to the negative 1. And what happens as b gets large? That goes to 0. So I guess my heuristic says no solutions. Okay, how seriously should we take this? Maybe only mildly seriously. I mean, an equation like this certainly could have a solution. But this is at least telling us it somehow is arguing against the idea that the number of solutions grows a lot as b grows. So I would say that generally a number theorist would look at this and say, I would expect there to be only finitely many solutions to this particular equation. I'm not going to say there's 0, but I am going to say that number of solutions doesn't grow. And by the way, here's a good moment. I was just talking to Carolina before we talked about this challenge that in algebraic geometry, we like to use homogeneous equations and so-called projective coordinates. And there's always a sort of choice of notation that can be a little confusing. So here's a good point, I hope, an objection that people are formulating, that if indeed there was a, and let's suppose, let me make this green. So warning, if let's say 1, 0, 1 is a solution. Oh, and it is, good. See, I was able to think of one on the fly. I'm impressed with myself. X equals 1, and z equals 1, the x to the fourth and z to the fourth cancel out, and then y equals 0 kills the rest of the terms. Well, then so is 2, 0, 2, and like 5, 0, 5, and like any multiple of that triple of integers is a solution. And that, again, it's kind of a fun exercise. It's because I made this thing homogeneous. That means that if I multiply x, y, and z by some constant lambda, then this equation just gets multiplied by lambda to the fourth. So if it was 0 before I scaled up all the variables, it's still 0 after I scaled up all the variables. So you may say, like, boy, your heuristic stinks because there's evidently infinitely many solutions. Okay, those don't really count. And when I say solutions, I'm always going to mean solutions up to scaling. So even though these look like different solutions, they all count as one because they're generated by this rather trivial procedure from some basic one. Oh, actually, sorry, I actually have this on the slide below, but now let me sort of say what I mean. What went into our heuristic here? Well, really only two things: how many variables there were, in this case 3, and what the degree of this polynomial was, what the homogeneous degree was, in this case 4. And why did we predict so few solutions? Because 4 is bigger than 3. And so you could use the exact same heuristic reasoning to say that an equation whose degree is higher than its number of variables would have, let's say, finitely many solutions. And of course, now I mean always in the sense of solutions up to scaling. But as I said, this is maybe not literally right. Well, I guess this issue of scaling I just addressed up here. So I guess with this little green addition, this part is not a problem. But what about an equation like this? This has x times y to the 6th minus 2z to the 6th equals 0. Well, that has very high degree, right? This is homogeneous of degree 7. But it has lots of solutions because I can let y and z be anything they want as long as x equals 0, right? So 0, y, z is a solution for all y and z. So here my heuristic seriously goes haywire. But you can kind of on some level see what goes wrong, that this polynomial factors, and there's one polynomial, there was one factor that's very simple, it's just x, and it's very easy to make 0. And so I hope you guys have that feeling, right? If you want something to be 0, if it factors into a bunch of things, that makes it easier for it to be 0, because if even one of the multiplicand is 0, the whole thing is 0. So we would say in algebraic geometry that this equation cuts out what's called a reducible variety. So there's an issue of what's called reducibility that can sort of get in the way of heuristics like this. All right, so now I'll state a big theorem and we'll jump off from there. So for a long time, I think it would be fair to say we knew almost except in specific examples. And then the whole world changed in the 80s after Falting's theorem. This is before my time. I'm senior now, but I'm not old enough to remember Falting's theorem being proved, but I'm told it was a big deal at the time in the 80s. That if you have an equation in 3 variables, again, by the way, I'll leave it as something to think about if you want to for fun, that homogeneous equations in 2 variables are not so interesting, or rather they are interesting, but they're more elementary than what I'm going to talk about. And the real fun starts with 3 variables. Okay, so I have a homogeneous equation of some degree d, strictly bigger than 3. And I also require that it be smooth. I'm going to say something about that in 1 second, but for now, just take it as a word. Then this equation does indeed have only finitely many solutions up to scaling. So this was the first really general theorem of this kind. and it made a huge impact. And let me say a word about smooth. And this is where I have to sort of to apologize for switching back and forth between notions of coordinates. We're geometers here, right? So I always say I've been talking, but what I've been saying so far sounds like I'm just talking about number theory. It sounds like I'm just talking about equations and their solutions, which sounds very classically number theory. Okay, in real life, people like me and Carolina, if we see an equation like this, we're gonna like draw its solution set. But you guys have already seen what happens if I try to draw something in 3 dimensions in the XYZ plane. And because of this invariance under scaling, it's really okay to sort of scale everything down so that z equals 1. You're still going to see a lot of what's going on with this equation. And then it's much easier for me to graph in the xy plane than it is for me to graph in xyz space. So for instance, if I take this equation from the previous page, x times y to the 6th minus 2z to the 6th, and I say, all right, let me just specialize to z equals 1. Now I have x times y to the 6th minus 2. And I can graph the 0 set of that function. Where is x times y to the 6th minus 2 equals 0? Well, it's 0 exactly when x equals 0 or when y to the 6th equals 2. And so you get, this looks like I just drew the x and y axes, but it's not. This is the x, this one is indeed the x axis, and this one is a translate of the y axis. It's the line y equals the 6th root of 2. Of course, the other thing that algebraic geometers like me and Carolina do is when we draw a picture of the solution set of an equation, we draw only the real points. Of course, really in our minds, we're thinking about the points over the complex numbers. And in the complex numbers, there's many 6 roots of 2, 6 of them indeed. Only one of them is a real number, so that's the one that I drew. So really, you should think of this as a horizontal line and then 6 vertical lines, but 5 of them are off in the complex space that I can't draw. All that being said, I draw this picture only to give you some sense of like why this would be a situation that's not smooth, because look at it. It's not smooth. Like, look right there. There's this part where 2 things cross and it's pointy and has a corner. So very roughly speaking, smooth says that no matter how you draw this picture, and if you sort of draw the points of this variety, of course, really you have to think about not just the real points, but roughly speaking, then nothing like this happens. And under that condition, which I'll emphasize, you can check algebraically, you don't have to draw pictures in order to check it. Then there is an upper bound, there's a finiteness statement what the heuristic tells you, because note 3 variables degree bigger than 3 is exactly when the heuristic tells you to expect finiteness, that's actually true. Great, okay, so that was like almost 40 years ago. So then what happens when you go up 1 variable? Like, let's now move on to the case of 4 variable equations. And I mean, sorry, everybody, this is just remains a complete mystery. And the class of equations in 4 variables where you can say something about what the solutions are. There are some very special ones where Falting's method will tell you something, and indeed Falting's theorem actually incorporates those, but mostly we have no idea. If I write down a sort of random high degree polynomial in 4 variables, you would expect it has only finitely many solutions. Absolutely no clue in the 40 years since Falting's how to prove a thing like that. It's a total mystery. Maybe let me take a moment to say, what about smaller degree? I said what happens when the degree is bigger than 3. And maybe here we're going to sort of introduce notation as we go, so I don't have to say the same things again and again. One way of dealing with the scaling is to just consider x, y, z, which are integers which are co-prime to each other, right? Because multiplying them all by 7 or something is going to give them a common factor of 7. So one way to sort of not have to say up to scaling all the time is to say now and forever, for all time, a solution means a triple x, y, z, where those coordinates have no prime factor in common. Done. We agree we're doing that? Okay, we're doing that. That's done. And then rather than saying every time, okay, the absolute value of x is less than b, the absolute value of y is less than b, the absolute value of z is less than b, I'm just going to introduce the notion that people in this area use, which is the height of a solution, which is just the maximum absolute value of x, y, and z, once written in their relatively prime form. So the height means the maximum of the coordinates. And now we're going to ask about solutions of bounded height. So what about when d equals 3? And again, for the number theorists, this is the case of what's called an elliptic curve, or a curve of genus 1. So here, Falting's theorem does not apply. It does not guarantee that there's only finitely many solutions. And indeed, there may not be finitely many solutions. But what is true is that if you count the number of solutions of bounded height, well, there's certainly only finitely many, because there's only finitely many choices of x, y, and z in that box. There's b cubed of them. Remember, we did that before. But the number of them that can be solutions to this equation is at most b to the epsilon. By the way, here I feel like I'm using like a little bit of analytic number theorist notation. So if you're not used to this kind of statement, what this means is that for every epsilon greater than 0, there exists some constant which depends on epsilon and also on f, such that the number of solutions of height less than b is this. So another way to say this would be it grows more slowly than any power of b. If you think there's some constant times b to the 0.00001 solutions, I'm here to say, like, no, there's not. I can show that it grows more slowly than that. In fact, I'm writing it in this way to make contact with a theorem I'm going to state later if I have time. But in fact, you can be even more specific and say it grows like some power of log b. So this is the case, by the way, where the heuristic we did earlier would be just beyond the boundary, and you'd be confused. You would say, oh, I expect b to the 0 solution. So this is epsilon. I know there's some analysts watching this, right? So like epsilon, you should think of it as like really, really, really close to 0, right? It's like that. It's like a very, very small, indescribably small real number. Okay, and when d equals 2, that's when our heuristic would predict lots and lots of solutions. And indeed, that's true, except there might be sort of some silly reason why there's not any. Like if I were to write down x squared plus y squared plus z squared equals 0, this, well, you may say, I can think of a solution 0, 0, 0. Okay, I forgot to mention that's not allowed. That's a solution to any homogeneous equation. So maybe I should say not all 0. We always disallow that. And if these are not all 0, this is a positive number. It can't be 0. So it could have no solutions, but barring dumb stuff of that nature, there's always lots of solutions, and it grows like the number of solutions of height b grows like b. So in some sense, there's a very satisfactory story. And so you might think, oh, I guess at least for equations with 3 variables, a lot is known. But now I want to take this in a different direction for the second half of the talk. And talk about a wonderful theorem of Roger Heath-Brown that had a big effect on me that came out when I was a postdoc. A theorem of Heath-Brown from 2004, which built on earlier work of Bombieri and Pila from 1989. And ready, here's the theorem. It's again homogeneous equations in 3 variables. By the way, I don't want to hide anything. This is what algebraic geometers call a curve. Why do we call it a curve? Because if you dehomogenize and set z equal to 1, you get a single equation in 2 variables, and that cuts out like literally, like its real points cut out literally a curve in the plane. So I don't want to hide what we're talking about. This is like what people would call curves. Shall I draw another one over here while we're here? Like if I were to write, like here's an example of degree 3, y squared z equals x cubed plus z cubed. If we set z equals to 1, you would have y squared equals x cubed plus 1. And that's like a very nice cubic curve like this kind of nice, smooth elliptic curve that we all like to draw. Okay, so a new theorem long after Falting's saying if I have a homogeneous form of degree d, the number of solutions of this equation, and I better say of height at most b, is at most constant times b to the 2 over d plus epsilon. Okay, now here's how I want you to respond to that, because I think this is how everybody responds when they first see that theorem. You should look at this and say, like, why is this a theorem in 2004? I mean, Falting's already proved that we know how to handle d equals 3 and d equals 2. D equals 1 is very trivial, by the way. And Falting's already told us that if d is bigger than 3, there's finitely many solutions. So this growth rate seems ridiculously weak. We're saying that the number of points of height less than b grows like b to the 2 over d. It doesn't grow at all. We know that by Falting. Okay, so the genius of this theorem is hidden in a place you might not think to look. So I'm going to circle it with my highlighter. It's right here. So why is this a theorem? It's because of this. It's because this constant, it depends on d and epsilon, but it does not depend on f. It doesn't depend on which equation you're studying. It's completely uniform over all equations of degree d. And that's quite amazing. So why is this a theorem? And I wanted to sort of write this with a flourish. That's why I didn't write it on my slide.
Jordan, let me just, there is a question here in the chat. Someone is asking whether the f is irreducible. Your f.
Thank you, because you do not need smooth for this, but you do need irreducible. And I did not think to say it, but you absolutely do need that. So it just means it can't be factored. So indeed, because the very example I already had on the board of x times y to the 6th minus z to the 6th, that has very high degree, and I gave you a very compelling argument that it has lots of points. So indeed, I need to say that. So thank you very much, anonymous YouTube chatter, for saving me from saying a false thing.
It was in the Zoom, actually. Yeah.
Oh, that was in the Zoom. Okay. But yeah, what's very cool about this theorem is that, for Faltings, all those high degree equations have finitely many solutions, but how many? It could be that, I write down an equation and it has like 10 to the 10 to the 10 solutions. I mean, there are some ways of getting upper bound, but they definitely depend on which equation you have. This one does not depend on the equation, only on its degree. And that has proven very influential and very useful. And it's just like a result of a fundamentally different kind than Faltings. The methods are different. The methods are actually much more elementary than Faltings. And I'm going to give you a cartoon of the proof in a minute. But maybe let me sort of stop and give a historical anecdote, because now we should get very greedy, right? If we know Falting's theorem, that there's this non-uniform bound that actually gives finiteness for the number of solutions, and we have this Heath-Brown bound, which gives a weaker order of growth, which is completely uniform and doesn't depend on which equation, you could just be greedy and say, like, por qué no los dos, right? Why can't I have both things? Why can't I have the finiteness and the uniformity? So here's a question. Is there a bound, if I have f, let's put in smooth, because I'm going to need that for Faltings, and of degree d, and I better say bigger than 3, where the number of solutions is bounded, not only is it finite, but it's bounded only in terms of d. By the way, smooth is going to imply irreducible for the people who were asking that before. So maybe I'll mention that, since we need that for. So here's a question. Let me, first, spoilers, we still don't know the answer to this question, but I will say, so yes, if you assume Lang's conjecture, which is a very big conjecture, a very big generalization of Faltings to varieties of any dimension. Or you might say, although this is not general enough, to equations in any number of variables. So this was a result, this implication was a result of Caparaso. I went out of alphabetical order to put my advisor first. That's not fair. Okay, let's put Caparaso and Mazur, which came out when I was in grad school, showing that if Lang's conjecture is true, then this bound on the number of solutions to an equation is true. Should you assume Lang's conjecture? Well, that is some dispute. This is not like the Riemann hypothesis or something. It's not like something everybody knows it's true, but we have no proof. I would say Lang's conjecture is much more controversial. And indeed, to give a little bit of social math history, this result came out when I was in grad school. And I think the feeling at the time was that this was implausibly strong, and that this implication meant that Lang's conjecture was probably false. That's how people saw it in the tea room. And so I think at the time, Joe Harris and Barry Mazur were basically imploring all the grad students, okay, go construct some families of curves that have more and more points. Go find equations of degree 5 or something and show that by cooking up a sufficiently complicated equation, you can make the number of solutions be as high as you want. And then disprove Lang's conjecture and be famous. Everybody wanted to do that. And then we tried and we tried and we tried and we couldn't do it. So now I think Lang's conjecture kind of came out of this somewhat unscathed, and maybe it's still true. I mean, we still have no idea. We have no idea whether this uniform is true, but I can say that if this seems implausibly strong to you, literally, if I come to you and tell you, okay, I write down an equation of degree 4 in 3 variables, which is smooth, and I claim there's never more than, I forget what the current record is, maybe 600 or something, and I claim, okay, it just can't have more than 600 solutions. You might say, really? Come on, if I make the coefficients large enough, I can find one that has more than 600 solutions. Okay, you should try. That would be a big deal if you could, but it remains a big open question. But if you could, well, I mean, beating 600 wouldn't be enough, but if you could show there was no bound, that would disprove Lang's conjecture. Okay, what are we gonna do in our last 22 or so minutes together? Let me give you a little cartoon of the proof of Heath Brown, because it's a beautiful argument, which is, in a sense, it's also a cartoon of Bombieri Pila. It's a very beautiful argument that's much easier than faulting. So let me sort of sketch how it works. Okay, ready? Here's the cartoon. Here's our solution set to f of xy1 equals 0. And let's suppose that there's lots of solutions. And okay, so here, again, this is the part where it becomes inconvenient that I'm switching from homogeneous to affine coordinates, but let's just bite the bullet and sort of say what I'm doing here. So if x, y, z is a solution to f, x, y, z equals 0, then x over z, y over z1 is a solution to f of, I feel like I should write these in a funny font, f of x comma y1 equals 0. And this again comes from the homogeneity. I almost feel like I should write this out in one case, just so we can sort of see it goes. So if I were to say x squared plus y squared minus z squared equals 0, the Pythagorean equation, I just want us to agree that that's the same thing as x over z squared plus y over z squared minus 1 squared equals 0. Those are just two different ways of writing the same equation, and it's from the homogeneity that always works. So this gives us a way of going back and forth between integer solutions to homogeneous equations, which is what I've been talking about, and solutions in rational numbers to equations in 2 variables, which is probably a little bit more the way most number theorists would think about. I mean, I even called the talk upper bounds on rational points, right? Because that's what the subject is called, rational points. I didn't call it integral points. Okay, so with that in mind, here's my curve in the xy plane, and I'm supposing there's lots and lots and lots of rational points all over it. Okay, I want to zero in on one little section of this curve, which is inside the red square, and then I'm going to magnify that and look at it with my microscope. And here's the thing about curves: if I look at a tiny, tiny, tiny piece of it with a microscope and blow it up really big, what does it look like? A line. That's calculus, right? That's the entire idea of calculus, that curves look more and more like lines as you look at them more and more close up. And so these points, which are close together on some little neighborhood of the curve, when I blow them up, I'm looking at points which are almost collinear. All right, that's kind of vague. What does almost collinear mean? Well, here's one way to think of it. It means that if I draw the triangle with these 3 points as vertices, boy, that triangle is really hard to draw, right? Because the points are almost collinear. Nonetheless, it's a triangle. And the area of this triangle, which again, I'm drawing a picture, but the area of this triangle is something you can compute by algebra. If you know the coordinates of the points. What is it? There's some 3 by 3 matrix whose determinant you compute or something. There's the area of this triangle is very close to 0. But on the other hand, so that's one fact. Okay, we're happy with that. On the other hand, if x, y, and z are all less than capital B, is what we call a low height point, then the denominators in these fractions are at most B. So on the other hand, if the denominators of the coordinates are at most B, this area is a rational number with denominator at most, okay, I think it's B squared. I don't remember if that's the area or the square of the area, but the exact power doesn't matter. It just matters that it's some rational number whose denominator has a bound. Okay. In some sense, I always say this is kind of like the deepest and most important fact in Diophantine geometry, even though it's very trivial, that there's no real numbers between 0 and 1. Sorry, there's no integers between 0 and 1. Sorry, I don't know why these notifications are popping up. I think that should fix it. So it turns out that if I make this little region small enough, I'm not changing B, right? I mean, I've decided to study all the points of height at most B. If I make this region small enough, I can make this area smaller than 1 over B squared. Okay, so if I have a rational number whose absolute value is smaller than 1 over B squared, and its denominator is at most B squared, what is it? There's only one choice left, right? It's got to be 0. But if the area is 0, that means the 3 points are collinear. And that actually tells you a lot, because what I've said is if I make this little patch small enough, then literally all the points inside this patch lie on a line. On the other hand, they also lie on this curve. And now we use the wonderful theorem of Bézout, which says that if I draw a line, the intersection of the line with the curve, the way I drew it, it only hits the curve twice, but in fact, that intersection has size at most D. There's an absolute bound on how many times a line can strike the curve. So once you get these points to be collinear, that gives you a bound on how many there are. And then what that shows you, if you make the patch small enough, you can show there's at most D points in that patch. You know the size of the patch, you know how many patches you need to like sort of cover some region of the curve, and then that gets you where you need to go. So that's the idea. I feel like I may have done that in a slightly too abbreviated way, but I hope I've given you the impression that in some sense, it's just linear algebra and being careful about computing determinants, which are the areas of these curves. And to make this work, I'll just comment that it's not really about triangles. You use what's called the Veronese embedding, where you embed it into a higher dimensional space by, instead of having your coordinates be x and y, you have them be all the degree m monomials in x and y. And then with when you're in a higher dimensional space, instead of thinking about the area of a triangle, you can think about, I don't know, the volume of a tetrahedron formed by 4 points, or the hypervolume of a hypertetrahedron formed by 5 points. And then you sort of optimize. I mean, Heath Brown is an analytic number theorist. So I mean, this is what these guys are very, very good at, right? Sort of like setting a bunch of parameters and then optimizing them all at the end. So he says, I'm going to embed in some larger dimensional space, and then you figure out which one gives you the best bounds. And in the end, you get the result that I stated. Okay, so now in the last 15 minutes, I want to tell you, I told you about these sort of two very different kinds of upper bounds, questions about their overlapping. Let me sort of say a little bit more about what's been happening lately. So first, I want to make the following remark. So here's an equation. X to the d minus 1z equals y to the d. Maybe I should try to draw a picture of this one. if I said z equals 1, that would be like x to the d minus 1 equals y to the d. I think I can draw that. It would be something with a kind of like a funny looking cusp right here. So it would be irreducible, but definitely not smooth. I mean, this pointy point right here is like really telling you, hey, I'm not smooth. And so Falting's theorem does not apply. Even though this has high degree, there's no guarantee that there's only finitely many solutions, which is good because there's not finitely many solutions. In fact, I can choose any integers a and b. I wrote d there, but I meant b, less than capital B to the 1 over d. And then you can check that a to the d minus 1b, and b to the d satisfy this equation. Okay, so how many choices do I get? A and b are each b to the 1 over d. So I guess in all there's capital B to the 2 over d choices, which give you many, many solutions to this equation. Well, you'll remember that that is the exact bound that appears in Heath-Brown. So not only is his theorem give like a really good uniform upper bound, but that upper bound is essentially sharp. You can't do any better because there are curves, not smooth ones, but irreducible ones, which give you that many solutions. Well, it's sharp at least up to the question of plus epsilon. He can't quite prove that it's upper bounded by b to the 2 over d. It could be like b to the 2 over d, some power of log or something like that. So let me comment, this is something I wondered about for a long time and like talked to students about and couldn't see how to get past it. But this was settled by Miguel Walsh, who's from the University of Buenos Aires in 2015. In actually a beautiful and rather short 10-page paper, he showed that indeed, and I think people were not sure whether this was true or not, he showed that the epsilon is not necessary. And in fact, there's a result of Heath-Brown type where you can just say, okay, constant depending only on d times b to the 2 over d. So that shows this is as sharp as can be because there's a witness. There are, I know I said I was going to talk about upper bounds, but an example gives you a lower bound. So there is a curve, the one at the top of this slide, an equation that has this many solutions. So this is best possible apart from the constant. Another thing that I always wanted to know because it's useful in applications is to understand what this constant actually is. And that was also a mystery for a long time until the very beautiful recent result of Kastrick, Kluckers, Dittman, and Nguyen just from a couple of years ago, showing that in fact, I mean, I'll say something about my work with Akshay in a second, but Akshay and I thought about this and we actually tried pretty hard to kind of explicitly write down what this dependence in the degree looked like. And it was hard even to write anything down explicitly. And it turns out that actually you get polynomial dependence, that you can get constant, absolute constant times d to the 4th times b to the 2 over d. I actually don't know. I just looked in the paper and couldn't find it. I don't know if they write down an explicit value for this constant, which would be sort of like the ultimate thing. But in any event, this is like pretty good. You know how it grows with degree. And actually they give examples. This example I gave gives you just like constant times b to the 2 over d. They have examples showing you can get 1/5 times d squared times b to the 2 over d solutions. So the only mystery remaining about this question now is the right order of growth in degree? Is it closer to d squared or is it d 4th or is it something in between? So that's a very satisfactory development. Okay, I'll get to say at least something about something that I did because, you know, we mentioned that Faltings requires smoothness. Okay, it doesn't literally require that, but the way I phrased it, it does. Heath-Brown does not, and you can see that the sharpness in Heath-Brown is witnessed by this curve, which is highly non-smooth. So one thing you could ask is, well, what if I tried to do Heath-Brown and get a uniform bound, but what if I gave myself the smoothness, made it a little bit more like Faltings? Would you be able to do any better? And the answer is yes, and this is when Akshay and I first thought about this, that we showed in 2005, that if you do give yourself this additional hypothesis of smoothness, and I should say, also, this is also in the d bigger than 3 case, then you can get some very slight improvement over to the exponent of 2 over d. You can show that the number of points grows somewhat more slowly than that. But this delta is pretty small, and it's pretty hard to work out explicitly. We did it, actually, this is actually true for d bigger than or equal to 3. And I think we worked it out for d equals 3, and it was like 1 over 180 or something. And for higher degree, it would be like even smaller than that. But there is some improvement in the power. And then finally, another advantage of this approach being more elementary is, remember, I told you that for faultings in higher dimensions, we basically know nothing. We know very little. There are very few cases of higher dimensional varieties where we can use anything like faulting's approach. By contrast, the Heath-Brown and Bombieri-Pila approach actually generalizes pretty well, but it doesn't quite say the same thing. So there's a wonderful theorem of Broberg, a student of Parasalberger from 2002, where in complete generality, he says, variety, and I had better, again, thank you, anonymous YouTube commenter, because this definitely needs to be an irreducible variety. So it's not like for the non-algebraic geometers, it just means it's not the union of two other spaces superimposed on each other. I guess I'm at the point of the talk where I'm going to have to use some algebraic geometry words for those who know. So variety is sort of a generalization of a single equation in variables. It might be cut out by multiple equations, blah, blah, blah. It's some algebraic space. But all you need to know is that the dimension and the degree, and you might say, oh, wait, can I bound how many points there are of height at most b? Not quite. You can show that if you look at all the points of height b, you can show they lie on a certain number of hypersurfaces. So what that means, let me draw a picture. Ready for another? This is supposed to be an algebraic surface, something of dimension 2. And it would be great if I could sort of give an upper bound on the number of rational points. But you can't really do that. But what you at least can do is say that there's some number of curves on this surface. And you could say all the rational points lie on these curves. But you have no control on how many lie on each curve. So the number of points could still be really huge, but at least you can say they lie on some union of curves, and there's this many curves. So it gives you some restriction on where the points can be. Okay. So in the last 5 minutes, maybe I will just sort of very casually state a result that hopefully will be up in the archive quite soon. We've written the paper. This is myself and Brian Lawrence and Akshay Venkatesh that just this summer. So here's the statement roughly as it is in the paper. We're going to have a variety which carries a variation of Hodge structure whose period map has 0-dimensional fibers. Okay, there's some set of people in the audience, Carolina included, who are like, oh, great, that's an interesting thing. And then like a larger population of people who are like, what are the words? What are we talking about? Let me try to rephrase it. Ready, here's for the topologists. For the topologists, I would say, let X be a variety so that if I look at its complex points, that complex manifold has a large fundamental group in Janos Kolar's sense, meaning that no subvariety of it has like a smaller fundamental group. Okay, so maybe the topologists are happy. They're like, oh yeah, like a thing with a big fundamental group. I can understand the difference between that and something simply connected. If you don't like that, let me say, and even simple, the sort of key example, which is our motivation in proving this theorem, maybe X is just the space of smooth hypersurfaces of degree d in n variables. Another way to say that is it's just the space of all homogeneous degree d forms, but subject to the requirement that their discriminant is non-zero. With the time left, I'm not going to give a general definition of discriminant, but it's like the following. This is sort of a trivial case for the point of this theorem, but like, what does a degree 2 and 2 variables look like? Ax squared plus bxy plus cy squared. And the discriminant is this thing that you know and love, b squared minus 4ac is the discriminant. And it turns out that this is smooth if and only if this discriminant is non-zero. So it's a wonderful sort of 19th century type fact that there's something like this. There's some crazy polynomial in the coefficients for any number of variables and any degree. There's some crazy invariant called the discriminant, which tells you whether the solution set is smooth or not. A wonderful piece of classical geometry. Okay, so I've sort of said something about the class of equations to which this theorem applies. And the result is that, and now here, because for the experts, this is not a projective variety, but only a quasi-projective one, I'm going to talk about the number of integer points, like solutions to integers of height at most b, grows more slowly than any power of b. It's on order b to the epsilon. And another way to sort of say the result of this in terms of hypersurfaces is that, or just in terms of pure algebra, if I look at the number of homogeneous degree d forms in n variables, and I should have said, all all coefficients less than or equal to b. So I'm counting in some huge box. I'm looking at all these forms, but then I'm going to put a strong requirement. I'm going to say, maybe apart from some set of primes that I've excluded, if I reduce it mod p, it's smooth. In other words, the discriminant is non-zero. So another way to say it is that if I look at this discriminant, not only is it not zero, but the primes that can divide it are restricted to this finite set S. And what our theorem shows is that that number grows very slowly with b. It grows more slowly than any power of b. Now, what's supposed to be true is that that set is actually finite. And in some sense, we're coming back to the beginning of the talk, because that's a form of what's called the Shafarevich conjecture. And the fact that this is true for forms in 3 variables is at the heart of the proof of Falting's theorem. So we would say in algebra geometric language, the set of curves of a given genus that have good reduction outside S is finite. That's Shafarevich's conjecture as conjectured by Shafarevich. Now people say all kinds of things are a conjecture of Shafarevich type. He used like dead and anti-Semitic, so we can sort of say whatever we want and call it the Shafarevich conjecture. So I'll just say that this is an area where a lot of work has been done, most notably by my 2 collaborators, Lawrence and Venkatesh, in their famous paper from 2018, but also by Javan Pekar and Lavran in 2016. And actually, while we were writing this paper, we found a paper last year by Brunebarb, which in some sense works very analogously to ours, but he's a true geometer. So there's nothing about rational points in his thing at all. He's proving things about sort of hyperbolicity of varieties and showing that they have no subvarieties that are not a general type. But in some sense, the spirit of his approach, which is aimed at a different problem, is very similar to the spirit of ours. So, and I said one idea about the proof, if time. It's pretty cool that I actually got here, like literally in the last minute of my allotted time. So I'll just say the following, that in the cartoon I drew of Heath Brown, I showed you that it was hard to stuff a lot of low height points into one very small patch of the curve. If you want to be a physicist about it, you could say, oh, the low height points like repel each other. It's like hard to stuff a lot of them into a small space. But the picture I drew, of course, was about a small space in the real numbers, right? In the real topology. As a number theorist, of course, I don't like to privilege the real numbers over any other completion of Q. And indeed, in the later work on Heath Brown, and even in Heath Brown stuff himself, you could draw that same picture, but using the p-adic topology instead of the real topology. And that is sort of the way this kind of thing is done. Hard to draw a picture of, but the same idea. And one way of thinking about the argument that gets our new result is that it reflects the fact that low height points repel each other. Also in a completely different topology, the topology of the space of sections, which, for the Grothendieck fans in the room, it's kind of like the Anabelian topology. There's this famous section conjecture of Grothendieck where you can put the rational points of a variety into some profinite space that comes from the Étale fundamental group. And that gives yet another topology on the rational points. And what we show, using in a critical way this result of Broberg, which is why I mentioned it, that the low height points repel each other in that topology too. And that extra repulsion is what you need to get a result that was unavailable before. Okay, we're exactly at the dot of, I guess it's 2 o'clock in Brazil, it's noon here in Wisconsin. So thank you guys so much. And Carolina, if there are more questions in the chat, I'm happy to talk about them.
Thank you very much, Jordan, for your very nice talk. So I'm waiting for some questions in the YouTube, so feel free to ask questions. And in the meantime, let me ask you something something very, very naive. So you've talked about upper bounds for those solutions for these equations. So what about lower bounds?
Oh, that's a great question. I think I mentioned one. I mentioned the lower bound in the Klucker and the Kaustrick et al. Paper that shows. So where is it? What's cool about lower bounds in this game is that you can get them from examples, right? So if you hope to have some upper bound that's uniform over all curves, and you want to sort of say like, where's the lower bound? You just have to show sort of one curve that has a lot of points in order to get a lower bound. But in general, it's pretty it's both hard and fun. So I mean, I think let me scroll back. Wait, so this open question is a good one in that respect, because if you want to get lower bounds, then your job is to come up with curves of a given genus that have lots of points. The way I set it up is about plane curves, but it doesn't have to be. And there are definitely people, including people not named Nomokis, who are like really good at sort of coming up with like really good examples with like lots of points. But in general, I mean, I think maybe one way of seeing why it's hard is that the way upper bounds are proved is like very non-constructive. It's like sort of saying you carve the variety up into pieces and then you show that the rational points repel each other in some way that there's not room to have like a lot of rational points in any one piece, and then you sum over the pieces or something like that. In order to get lower bounds, you actually have to construct solutions to equations, which is pretty hard. And in some sense, we only know how to do it by some version of starting with the solutions and sort of putting an equation through them in some sense, like sort of putting them in very artificially. It brings us back to the very original question that if I just write down some equation, how are you going to construct a solution? Basically, all we know how to do is sort of set up our computer to test many, many, many values and see if, I mean, you know, apart from very, very special classes of equations, we just have no way, to do it.
Thank you, Jordan. So I don't see any questions here at the YouTube. There is a question here in the Zoom. Is the analogous problem number of solution less strict than CD for curves or function fields meaningful? Is it any easier?
Oh, that is a great question. And I would say I'm pretty sure that's not known. I always think it's easier over function fields, but it varies a lot how much easier. Faultings itself is easier over function fields than it is over number fields, because there's a lot of sort of really gritty stuff about the faultings height that goes into faultings proof that is not so hard in the function field setting, like stuff that has to do with the Archimedean place. But yeah, that's a great question, and I don't quite have an answer off the top of my head.
Thank you, Jordan. So I don't see any more questions in the YouTube, nor here at the Zoom.
Awesome. Well, thank you guys so much for having me, and I look forward to the rest of the conference.
Thank you.
Bye, guys.